Hi, and welcome to another Hopper on 6502 video. In this one, I'm going to talk about the serial EEPROM that's on board. So when I originally designed the board, I made it for these 512 kilobit or 32 kilobyte EEPROMs, but they're pin compatible with so the 32s are compatible with the 64s and the 128s as well. And this goes into the socket over here and it's I2C. So let's have a look at that. So the smallest one you really want to use is this 512, which is 512 kilobits or 64 kilobytes. And it has 3 address pins, A0 through A2. So that means you can have an address from 0 to 7. And by default, these serial chips, these serial EEPROM chips, are at address 50 hex, which means you can configure these EEPROMs to be at 50, 51, 52, up to 57, right? So I just figured it's okay to set all those to 0. So in my board design, I just set them to be 0. So all my address lines are just put to the ground plane. What I didn't know at the time when I made this board was that if you get the 128K version, there's a little asterisk next to the A2 here. And it says it should always be tied to VCC, in other words, to positive. And the reason they do that is because if you look at the whole protocol for how you communicate over I2C with these things, the address is 16 bits. So with 16 bits, you can only address 64K. So the way they got around it was they made A2 be special. So it's still pin compatible. You can plug it into one of the other, you can interchangeably use these ICs and it'll just change the capacity of what's plugged into your board. But by making this pin too high to VCC, it makes it behave like 2 different 64K serial EEPROMs. So what it means is this high would be bit 2, so value 4. So if you make this high, the address would be 54 hex. So, but internally, if you address, so this isn't actually addressable. If you internally then address it as 50, you get the first 64K bank. And if you address it as 54, you get the second 64K bank. So what did I do with my board? When I put in one of these bigger ones, I bent up the pin on the chip and tucked it over to 5 volts. So without modifying the board, instead I just modified the chip. And that means I can use 128K EEPROM on the same board. And Hopper doesn't know the difference. Hopper still sees the 64K version at I2C address hex 50. But there's a second 64K now available at hex 54. And that brings us to today's video. So now that I have a second 64K, what can we do with it, right? So in the start of this program, this is my demo program, I configure something called block storage at that address. And I tell it I don't tell it it's a 1026. I don't tell it it's the 1024 version. I tell it there's a 64K version sitting at that address because that's the 64K version. And the reason I do that is because it means the page sizes will be 256 bytes. So it'll have 256 pages of 256 bytes each, or I call them blocks. So let's go have a look at this block storage. This is what I've just recently written. So I added a new folder under the library. There's a file folder. And because the Hopper minimal runtime didn't have file or directory like the microcontroller Hopper has file and directory, and Windows Hopper has file and directory. On Windows, obviously, it uses your disk drive. On the microcontroller, it uses the built-in flash to have a file system, and it usually uses a file system called littlefs. For the 6502, I added this extra file folder under library, and inside that folder, there's another 2 files as well. There's serial EEPROM and block file system. So serial EEPROM is the stuff that does the I2C, and it's got a configure that we've already seen. We've called that with the address, and then just a write block and a read block. And I've made it so that you could use this with 512 byte blocks as well. So you could use it with the 1024 kilobit as well, but we're using this one today. And that's all this thing does. It's only got like 3 or 4 APIs in it. It's read block, write block, and configure. Right? Control backspace to go back where I was. So that's the serial EEPROM. So all it exposes is the ability to read and write a 256 byte block. Then a couple of months ago, I wrote a C-style file library for I2C, which actually used this serial EEPROM, but instead of having Hopper in this EEPROM, I had your I2C program, which you have to burn every time you make a change to your I2C program. So not as convenient as Hopper, but I made a C-style file system for this I2C before I knew I could get a second one out of it. So what I did in the last couple of days is I ported my C-style, it's like a file allocation table style system, and I ported it from I2C to Hopper. So it's about 1,300 lines of code, and it's sort of very C-like, but it's obviously written in Hopper. And it's got all these methods that look like C methods, like fread and fopen and fcreate. Fopen, fclose, fread, fwrite, seek, tell, all the usual C APIs. Remove. It's got mkdir and that sort of thing, like make a directory, remove a directory, all that stuff. And C modes like read and write. So a C-style file system. So what do we got? So when you upload your Hopper program to persist it from one run to the next, the Hopper program goes on the first 64K block, the one that at hex address 50. The second 64K block, which is at hex address 54, is now being occupied by this file system. And it's all written in Hopper. So I didn't change the Hopper runtime at all. I wrote the whole file system in Hopper. So the guts of it is this 1,300 lines of stuff I ported from my I2C version. And then I implemented a file unit and a directory unit, and they're just little wrappers around the private methods of this thing. So private methods have a lowercase first character, but if I say friend directory and friend file, it means that from the file or directory unit, you can use the private methods in file system. And the reason I did it all this way is so that I can easily replace these two with another block file system. So, for example, if I just replace serial EEPROM with an SPI interface to read and write from an SD card, I could write a simple file system that worked on SD cards as well. And all the rest of the code would be unchanged. It wouldn't know that the underlying media is an SD card and not a serial EEPROM. But anyway, all the usual file APIs in Hopper are now working. And the Hopper file APIs are much nicer to use than the C ones because they sort of, they don't fail. They're sort of atomic at the expense of being sort of inefficient. So what do I mean by inefficient? Well, if we look at open, so open is used to read a file to open a file for reading. In Hopper, if you're opening it for writing, that's called create. So let's look at open, which is open for reading. I'm right-clicking on things to jump to them. So what does open do? It converts your path into a full path in case it was a relative path, and the full path uses the current folder if you've got a current folder or whatever. So it'll resolve your path to a full path, and then it'll try and open it. And if it exists, it'll end up with a file handle. And if it didn't, it's going to say file not found. If it returned an empty file handle, that's the equivalent of null. The first byte of the file handle is 0. If it succeeded, it'll loop through the file reading at 128 bytes at a time, and it'll build a string. And that's what this buffer is. It's a string, the file instance buffer. So when you open it, actually reads the whole file and loops around till it runs out of bytes, and sets up this file, and it sets up a position in the file, which means from now on, none of those you can now read from the file like a byte at a time or a line at a time, and it won't access the hardware again. So it does all the hardware access in open. Creating it, so that's how reading a file works. So all the other methods just read from the buffer after it's been loaded. Writing a file works very similar in Hopper. So if we right click on create, create will delete the file if it already exists. So it's going to overwrite it with a new one. And then it just sets up the file instance record to start creating the file. It doesn't actually write anything to the system, just deletes it if it already exists, right? And then to create, you'd go and look at what append does. So append will add to the buffer of the current file instance like this, just keep adding to the buffer. So it doesn't actually flush it to disk. And then to finish writing, you need to use flush. So I called it flush rather than close because you might not know what a close does, but you're pretty sure what a flush does. So flush is the part that does all the writing. It's the actual writing to disk. All right. So let's see how we use these. So as a test program, I wrote a little console, and it's like everything's baked into the same file. So the whole test program's like 300 lines, and it just reads a line from the IO from the console. That's the serial console. Sees it if it's a command, and if it is, it executes the command. So enough of that. Let's build this. So pre-processing. Just noticed we can't see the bottom of the screen in this screenshot, but that's okay. Wonder if I can fix that. Yeah, that's better. Now we can see the whole screen. Oh, I know why it is. Let's do that. Let's see if I can do that again with the full screen. No, still can't see the bottom of the screen. Okay, I'll do it outside full screen just for this. I'll figure it out later. Don't know why my video is not projecting that bottom status bar at the bottom here. So anyway, if I build here, you can see the build steps going through here. Pre-processing, compiling, optimizing, all that. Right. And I have my device connected and ready to go. So if I go F5 here, it'll load it says uploading, and the debugger says it turned to green there. And I'm running in the debugger right now. I'm going to make that slightly smaller. And then if I control F5, we're running in the debugger. So you'll see up top here, right, this is the serial console. We got our little, our console here. And I might have some files here. So if I dir, it's pretty slow because I'm running in the debugger and because it's on the 6502. So if I format, I should be able to clean the drives formatted. And if I say help here, it tells me what commands are available. I can exit out of here and run it full screen so that so it doesn't wrap around like that. So if I ran from full screen here, let's see what that looks like. So uploading the program and running it. So now, there we are. So there's our console. There's a help. And because I formatted it, that folder should be gone now. There should be nothing. There we go. And now I can say, make me a directory called folder. And then you'll notice the blue light goes on when the command starts and the blue light goes off when the command's finished. Now I can say change to folder. And there's a create command. Oh, it's not listed on the help, but there is a create command, and I can create a sample file. And line 1 in the sample, line 2 in the sample. And if I give it a blank line, it'll finish. So now if I go dir in this folder, it's got one file in it that's 46 bytes, and I can say show sample. There we go. We have our lines of our sample. And if I go back up to cd ... and I go dir-s, it'll give me a recursive directory. So it should show me folder and the contents of folder as well. There you have it. I've got some diagnostic tools, so I can say show me block 0. And block 0 is the 256 byte file allocation table. The first byte is completely unused because it points to itself. So I put the value 42 in there, decimal 42 or hex 2a, you know, the answer to life, the universe, and everything. And that's how I can detect if you configure an EEPROM that doesn't have this magic number in it, then it'll automatically format it when you first configure it. And we can see we've got 3 blocks allocated. It's just 1 or 0 to say if it's allocated or not, and it puts them in chains, so you can have files bigger than 256 bytes and chain them together, or directories with more than, you know, with a lot of entries that don't fit into one block. The first block is the root directory. There we go. And the root directory has directory entries are 16 bytes long, so file names can be 12 bytes, and then the last 4 bytes are used for the directory data. And if we look at block 2, we should see this is the root directory, and it says this 2 here indicates that this other directory, the folder, the directory called folder, is in block 2. So let's have a look at block 2. And in block 2, there's only one thing. There's a file called sample, and again, it tells us where it is. There's also a bit here to tell us that's the length of the the file name is the lowest 4 bits, and the highest 4 bits is a 1 if it's a folder and a 0 if it's a file. So let's go to folder and let's create another one. Sample 2, another one, and that can be 1 line long. So now if we go dir, we'll see we should have 2 samples, one smaller than the other. And if we look again at block 2, we should now see a second directory entry. And if we make a subfolder in here, then look at it again, and then look at what's in that block again. So now we've got the subfolder, sample, and sample 2. We look at the block, and subfolder is the 3rd directory entry in this directory. And you can see it's got a 1 in this slot here to say that it's a folder and not a file. Right, so cd to the root, dir-s to do a recursive directory again. Anyway, the main purpose of the demo was of this demo program is to sort of exercise all the features of this little file system. But if you were going to use it to persist data inside your Hopper program now, you'd obviously use a lot less functionality than this. So for example, we could go and extend Tigger Basic now to be able to load and save files to disk. It would be a good example of how to use this. And at that point, we'd probably just put them all in one folder, and we probably wouldn't need much in the way of functionalities. Let's exit out of here. What did I want to look at? Oh, I was going to show you how you initialize. So yeah, this is how you format. You just mount it with true. True means always format, whether it's formatted or not. If you mount it with no argument, let's have a look at that. If you mount it with no argument or false, then it'll look for that 42. And if it's 42, it won't format it. But if you mount an unformatted serial EEPROM, it will format it. And by formatting, all it does is clears the file allocation, which is this chain block, block 0, and clears the root directory. That's all that formatting does. So in theory, you could recover stuff from a formatted drive because you could go hunt around because it doesn't touch the other 254 blocks. Anyway, back to the plot here. Go to the Hopper main program. So how do you use the file system? You initialize I2C. You configure your block storage, telling it the address and telling it the size of the EEPROM, and you want a 64K one at 5.4 in this case. And then you mount it. And that's it. That's these 3 lines, initialize your file system. And then you can do things like, use all these commands. And this sample shows you how you would do any one of these things. Like, let's go and have a look at create, for example. How did I create the file? Like I created a sample text file. So what did I do? If you try to create a file that it already exists, it fails. If not, it creates the file. And then it reads lines of text from the console, from the serial console. And if it hits an empty, if you hit enter with an empty line, it finishes the file. If not, it'll append that line plus an end of line to your content. That's the append there. And then when it's finished, it flushes. So that's how you create a file. And then how you would read a file would be if you just go and have a look how show is implemented. So, it first checks to see if it's existing or not, and then it opens it, and then it reads lines. And this is a thing in Hopper. The file APIs do not return an error value, and I did that because I didn't want to overload return values. Like the C APIs will return -1, or like if you try and open a file that doesn't exist, it'll return a null. And I don't like overloading the return value with an error value. So instead of that, every time you call a file API, you can immediately check if the file is valid or not. So I opened the file, and then I read from it. So even if the open failed, then this read line would fail, and there's no crashes or anything. It just means that when I call valid, it'll say false and break out, and we're done. If it is successful, it did open a good file. It probably will because it checked if it existed. This will read the first line, which means it reads bytes until it gets to an end of line. And then it'll output that line and wrap around and try it again until it gets to the end of file, in which case it'll be invalid and it'll jump out. Let's go look how read line is implemented. I'm right-clicking on read line. So read line verifies certain things about the file record, like it checks that it's not open for writing. It checks that it's valid. So the reverse of all these conditions. So if any of these things is true, then it's not valid. So if we're not reading or we're writing or the file isn't valid, then we're not valid and we should exit. This looks like cut and paste. I just did it twice. Well, we can clean that up. Okay. If the position of the file in the file record is greater than or equal to the size, that means you've read beyond the end of the file. Therefore, we're invalid and we exit. Otherwise, we're in good shape. And then it loops through here, like while we're less than the end of the file, get a character, add it to our, and we're going to add it to our buffer here if it's not end of line. If it's end of line, we break out. So this is how we read a line from the file. And when we get the last line, it'll just switch to invalid. And this file record that I'm talking about is actually a Hopper record structure. So there you can see the buffer that got read in. You can see the position, the current position of the cursor in the file, and the size of the file, whether the file was open for reading or writing, all that sort of thing. And if you go and look at the directory, it's got something similar, but directories are obviously simpler. Just is it valid and what's its path when you opened it. And then with directories, you can iterate them. Let's go have a look at how dir is implemented. So there's a second call because of the recursion possibility. So you can do a recursive call. And the recursive call, calls this itself again. but let's ignore that for a second. So when you're given a directory to do, a path to do a directory of, you open the directory, you check if it's valid. Then you can count how many directories are in the directory, in other words, how many subdirectories, or you can count how many files are in the directory. And then you can iterate through them and say, get me the file. And it doesn't get you a file handle, it just gets you the path of the file. So it was also supposed to be like, I didn't want a file system that relied on having a fixed number of handles that you could support and having to store the handles somewhere. So I just use these records and then the path. I pass the path around a lot. So once you know the path of your file, you can then open it using the path. And the same is true of directories. How many are there? Get me the directory, it gets you a path, and you can do other things with it, like recursing it. Anyway, I thought it was pretty good use of that EEPROM, and nice that we can actually extend the existing board without making any serious changes. If only if I did a revision, I'd make that pin high, because it just would mean, but by default, a 64K serial EEPROM would have to be at address 5.4. Or I could switch them around so it's always at 5.4, and then make the second, the temporary storage one be at 5.0, and then you'd only have one version of Hopper that always just looks for the current loaded program at 5.4. But this works for now, just bodging the chip like this. Just, I'll show you again what I did there. I just bent up one of the pins and tied it to 5 volts on the other pin, which is the 5V power supply pin of the device. All right. Thank you for watching another Hopper 6502 video. And don't forget to like and subscribe. And this video is part of a playlist. If you're more interested in this, you can watch the whole playlist. Cheers.